is there any kind of optimization that we can do based on total bridge weight and the total deflection?
Okay. For the steel bridge competition in particular, optimization might be a little bit more difficult, but STAAD Pro can perform an optimization. Let me show you what we have for that. And maybe this applies to your steel bridge, or it would definitely apply to just steel design in general.
Okay.
Okay, so I just happened to open one of our bridge files. And what we do have now, I believe for this training class, we brought you up through the point of analysis and looking at analysis results. We didn't take you the extra step of actually performing the design. Now, STAAD Pro can perform designs on steel members, and what we do is, I think we brought you up to the point that you would need for this bridge competition through this analysis portion. But in a realistic structure, you would want to do the next step, which is actually design the structure. So you want to find out if your structure is passing or failing, what your interaction ratios are, and even if the program can do optimization, giving you more efficient shapes than what you initially provided. To do that, what we would want to do is our typical workflow in STAAD is, this is our page control over here, and we always want to work our way down. So our last step is design. And you can see here I'm on the Design tab and the Steel sub-tab. And now I have several options for design. One of the things I want to let you know of, though, is the reason we didn't take it through that full design portion for the training manuals is because we know that a lot of the sections that maybe you're using for your steel bridge competition are not standard AISC sections. So if you want to do a full design or optimization, you're going to need to use standard AISC sections because STAAD will perform designs on those. It'll always, you know, like if you have like a steel rod or something, for example, in your steel bridge, you can always get your member forces, you can always get deflection results, nodal deflections and stuff, but it actually won't design something unless it's a standard AISC section. If you're designing something for maybe another class, or maybe you are using standard AISC sections in your bridges, then you can definitely perform a design in STAAD Pro. So your steps to do that would be, after you perform an analysis, and that analysis command always needs to be included for no matter what, you would then go to the next step of selecting this Design tab and then the Steel sub-tab. And here we have several different codes available, so we'll stick with our most current one, AISC 36010. You'd want to define any relevant parameters for your structure, things like yield strength, deflection ratio limits, since I know you asked about deflection, interaction ratio limits. The default for that, of course, is 1.0, but you can go a little bit more conservative if you want. And that is done through this process here, this define commands. And then after that, we follow that up with a command structure. So let's go over to this commands button, since you asked about optimization. And we have several different options here. Your simplest and most direct form of steel design is just perform a simple code check, which basically means that you assign steel sections to each member. And for these kind of commands, we're going to want to use standard AISC sections. And it'll just give you an interaction ratio saying pass or fail. If, however, you want to perform an optimization, then instead of selecting code check, you can use this select command. And this is basically our way of saying perform an optimization. So what it'll do is you always need to assign initial section sizes to every member in the model, even if you're planning on performing an optimization. The reason for that is because STAAD Pro needs that type of information to determine the self-weighted structure and the stiffness of your model. And then the select command will say, okay, it'll go through and check all of those, and then using that force distribution from those initial sections, it'll go through and give you a more optimum size, which may be bigger or smaller than your initial size, but it'll give you the one that gives you an interaction ratio closest to 1.0, you know, as an alternative section. And then there's, you know, a few more steps that you can follow after that, but we can do all of that, and you'd want to do something more like the select command in order to do that. But yes, we can do that, and this would be on standard AISC sections. If you're using steel rods, then you're probably going to have to do some of that process more by hand.
Yeah, I was wondering also the code check I know I can perform on members that I have defined, even if I define like a very thin rectangular tube or something that isn't standard AISC.
Okay.
And I noticed that I can do a code check on that. Is that reliable if it's like I'm specifying a very thin tube? Is that reliable? And then could also that be included on the optimization?
Okay, yes. So instead of doing this section's database up here, did you do this, or did you do this define button to assign the size?
No, I did. I chose over to the left, right above HSS rectangle, pipe and tube. And then to the right,
okay.
I did define tube and defined the diameters and thicknesses.
Okay. So anything you select through this section's database button should be able to be included in a code check. When I say non-standard AISC sections, that would be if you went over here to this define button and defined just a simple rod. Then it doesn't quite know what to do with that as far as a code check goes. But if you're defining something through here, through the section database area, usually I would definitely say your results are going to be accurate. If you're doing something like this where you're defining it, I'm not sure, to be honest, if it could do an optimization on that. Because what happens with the optimization is you can give it limits on the optimization, but what it's going to do is it's going to search for an alternative within the same family for which you initially assigned. So here up here, if I selected a standard W-shaped section, it would look through the W-shaped family to assign an alternate size. Now, if I do something like a pipe, like here, so you didn't use a standard pipe, you used a defined pipe.
Yes, ma'am.
Over on this side.
Mm-hmm.
Okay.
And it does work in the code check. You know, I just wasn't sure if I could really trust it down to, 0.98 ratio or whatever. I don't know how accurate if it was or if it was kind of over judging. Because I noticed like I would define very skinny pipes sometimes, and it would accurately like just go ahead and give me 0 for inertia values, IX, IY, IZ. It just after or beneath a certain diameter, it just went to 0. So I guess that is slightly conservative, but I just didn't know if it was really set up to do code checks with that small members.
Okay. I believe a code check should work out for you. If you're defining it manually, it might not know how to use that select command because it won't quite know where to search for an alternate size for.
Okay.
So I'd say your code check probably works fine. If you do want to go with something a little bit more conservative for a code check, say you're a little concerned about maybe something that's at 0.98 and you want to build in a little extra there, what you can do is in this steel design area, if I go down here to define parameters, which you'd always want to define your parameters before adding that code check command, I have a ratio option here, and the default is 1.0. If, say, you wanted to set this value to 0.95 instead, say, okay, I'm going to let everything get up to 0.95 because that's what I feel comfortable with, you can do this, and then it could flag any member that's over it to give you a little bit more information or options. So, I mean, you could always do that. I'm not sure if the select command would work. My guess is probably not if you're defining your own custom size.